Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to your YouTube channel Chandan Physics. In this video, we are going to discuss quantum Virial theorem. Let's begin. In classical mechanics, the Virial theorem states that k bar is equal to minus half summation over I ri vector dot fi vector its bar. Means bar indicates the average factor. K bar means the average kinetic energy of the system of particles. There will be a system where a number of particles are there. We consider the ith particle and its position and the force executed to that of particle. Therefore, Fi be the force acting on ith particle at the position Ri. This is the quantum Virial theorem in classical mechanics. But the average notation in classical mechanics, when we transform to that of quantum mechanics, the expectation value play the same role as that of average factor play in classical mechanics. The expectation for that observable play the same role. That means in quantum mechanics, the quantum Virial theorem states for that of particle when the system is at stationary state, the particle is in stationary state. Therefore, k expectation that for stationary state is equal to minus half r dot a vector of that of expectations stationary state. We have to prove the quantum Virial theorem. Now we have to prove that one. How to prove? By using the concept of HEISENBERG'S equation of motion or constant of motion in quantum mechanics. What is that HEISENBERG'S equation of motion in quantum mechanics? As we know, if q expectation, or we can say q cap is the operator that represent for that of q, therefore the rate of change of that expectation value will be minus I by h cross the commutator bracket of q cap h cap expectation plus the expectation of del q a del t. To solve that type of equation, means the quantum Virial theorem, we have to put x px in place of q. Let us substitute. Let q is equal to x px, means that term doesn't depend on time explicitly. That means its differentiation with respect to time, that is x px, will be 0. Then just put x px for that of q value. Therefore, d by dt of x px expectation is equal to minus I by h cross x cap px cap h cap commutator bracket and its expectation. Now, what is that of Hamiltonian? Let for a particle of mass m, for a particle of mass m moving along x direction, in a potential of Vx, then the Hamiltonian is h cap is equal to px cap square divided by 2m plus v cap x. Therefore, that commutator term will be expanded like this: x cap px cap h cap commutator is equal to x cap px cap. In place of Hamiltonian, we substitute px cap square divided by 2m plus v cap x is equal to 1 by 2m x cap px cap square plus x cap px cap v cap x commutator. Now we have to expand these two terms individually. First that commutation bracket, then that commutation bracket can be solved. Now just I introduce that as equation number 1, that let equation number 2. Now 1 by 2m x cap px cap square commutation relation is equal to 1 by 2m, that is x cap px cap square plus x cap px cap square px cap. This commutation relation will be 0, only that commutation relation exists. 1 by 2m x cap px cap square commutation bracket px cap. Now we expand it like this: 1 by 2m that is written like this: 2 px cap x cap px cap commutation bracket, then px cap. Px cap means px into px, 2 times it will be achieved, then I say it as 2 times multiplication of that one. Here that is 2 cancel out, that is px cap square divided by m x cap px cap commutation bracket, that is x cap px cap commutation relation between position and momentum px cap divided by px cap square divided by m into I h cross, that we have I h cross px cap square divided by m. Next term, second commutational relation. Again you have to solve second one. Again that is x cap px cap b cap of x commutation bracket is equal to x cap as px cap b cap plus x cap b px cap. Its commutation relation x cap b cap commutation relation will be 0, means this one is the potential term, these two are the commutation relation between position and that potential will be 0. We exist x cap px cap b cap is equal to, now we have to solve that one. So to solve that one, we put a wave function, let's say. Therefore x cap px cap v cap act over a wave function, let psi x. What will be that value? That is x cap, here px cap v cap psi minus v cap px cap psi is equal to x. Px cap means h cross by I del by del x of v cap psi minus here h cross by I v del psi by del x into x is equal to x h cross by I. These two are multiplied with each other, that means we use the product rule of differentiation, del v by del x into psi plus x h cross by I v del psi by del x minus x h cross by I v del psi by del x. These two terms x h cross by I v del psi by del x cancelled out, only that term exists. H cross by I can be transformed to minus I h cross x del v by del x psi. Since psi is arbitrarily chosen, therefore since psi is arbitrarily chosen, we have x cap, sorry, that is the expectation of, very sorry, that is x cap into px cap, these two are multiplied, x cap px cap psi x, x cap px cap v cap of x is equal to minus I h cross x del v by del x. This is the second one, means that commutation relation. We have to put these two results of these two commutation relations in equation number 2, right? Putting these values, in equation 2, we get it is x cap, px cap, h cap, permutation bracket of expectation will be I by h cross divided by m px square expectation for that of stationary state. Here we consider the system which is stationary in state, minus I by h cross IH cross x del v by del x at stationary state. Then what will be the values? Just multiply and divide 2 here, 2 IH cross divided by 2m, there will be no such change, px square expectation for that of stationary state minus I by h cross x del v by del x expectation that of stationary state, it is 2 IH cross px square divided by 2m expectation for that of stationary state minus I by h cross x del v by del x expectations for that of stationary state. For that of stationary state, we say for that of stationary state we consider for stationary state the expectations rate of change means del by del t of q expectation for that of stationary state will be 0. Here we choose x px as q, that means that term will be 0. Therefore, we have 0 is equal to 2 IH cross px square divided by 2m for that of stationary state minus I by h cross x del v by del x expectation for that of stationary state. This factor to that side, or we can write in a simple manner 2 I h cross px square divided by 2m stationary state will be IH cross x del v by del x is expectation for that of stationary state, or IH cross cancel out, again px square divided by 2m stationary state is equal to half x del v by del x expectation stationary state. Now generalizing this equation in 3D, what we have? Generalizing this to 3D, we get means p square divided by 2m, its expectation for that of stationary state is equal to half r dot grad v expectation for that of stationary state. This factor is known as the kinetic energy term, that is k expectation at stationary state is equal to minus half r dot f expectation stationary state, where f vector, that is the negative of potential gradient, and k kinetic energy p square by 2m, k be the kinetic energy of particle, that is the kinetic energy of particle having mass m and momentum p. This is the usual equation, that is quantum Virial theorem. This is the equation of quantum Virial theorem. So, with the help of this visual lecture, we understand what is Virial theorem in quantum mechanics. This is the equation for that of Virial theorem for classical mechanics. We transform it to the Virial theorem in quantum mechanics and its proof by using Heisenberg's equation of motion or constant of motion in quantum mechanics. Just put xpx for that of q and simplifying the commutation bracket relations, implement the Hamiltonian factor here. These two commutation relations are solved. First commutation value IH cross px square by m. The second commutation value is easily solved out, that is that one. Now putting these two values, for that of stationary state, that value will be 0, each sides are simplified as that one, that is for 3D, and finally we achieve the Virial theorem in quantum mechanics. So, with this useful and informative notes, let me wind up this session. Thank you.